Hey everybody, I just wanted to record a quick video to share something I've been working on for the last couple of days. Um, I've always thought that signed distance fields are really fascinating. They're widely used in the demo scene to produce really cool 3D graphics, and I guess I like to think of it as kind of like signed distance fields are like the functional equivalent of 3D graphics, as in like if polygons are imperative, then SDFs are kind of like functional 3D graphics. Like the really interesting property that they have is that you can combine them really easily. Like it's really easy to like subtract a shape from another shape and do these kinds of like CSG operations on them. One downside that they have though is that they're really expensive to render because you need to do a lot of sampling of the function that you're rendering, and like the naive algorithm to do this is called ray marching or sphere sphere tracing, I guess, and it takes like a lot of samples per pixels. Like here, I have a cube, a rotating 3D cube where I'm subtracting uh, three cylinders to create this shape that's like 100% defined by this implicit sign distance field. Um, but yeah, this is rendering on a single core on a Mac M1 laptop, and as you can see, it's like I'm doing approximately like 9 evaluations of the function for each pixel, and I'm getting only like 13, 14 frames per second. There is a slightly better algorithm that uses less sample that uses over-relaxation. And yeah, if I press the 2 on my keyboard, I switch to this like accelerated ray marching, and I'm making less samples. As you can see, if I toggle between like standard and accelerated, I'm taking less samples of the SDF. The problem is like on CPU at least, it's not really faster because the algorithm that uses over relaxation is a bit more complex, and so the algorithm itself is a bit more expensive. So I guess what I'm trying to say is like reducing the number of samples of your SDF function is more beneficial when your SDF function is really expensive. But for a function that's comparatively inexpensive, like this might not actually be a win. But so something I've been thinking about for a while, like I actually published a blog post in 2016 about how it might be possible to use partial evaluation, which is a technique from compilers to kind of optimize the SDF to take less samples. So the idea is like most of the space is actually empty, right? So you shouldn't really you shouldn't be wasting like a lot of samples per pixel sampling empty space. And if you could use compiler techniques to like prove, for example, that this cube doesn't exist in certain parts of the view frustum, then you could totally avoid sampling those parts of the screen. Um, Unfortunately, I never did implement that. I think like one of the downsides is like that's pretty algorithmically complex, and yeah, and it's actually not that trivial to do. But more recently, I had an idea, which is that uh, you you could use a recursive algorithm. Like this is more practical on CPU than on GPUs, but like on on a CPU, like you could think, for example, at first you sample array at the center of the view frustum, and you try to advance as far as you can towards the object. And when you can prove like that all of the corners of the view frustum are, well, okay, so let me rephrase that. Like if you take array at the sample of the view at the center of the view frustum, uh, and you take a first sample of your SDF, you you can advance all of the rays at once towards the object, right? And after that, well, you could keep going for a while, but like if you can't safely advance all the rays in your view frustum, then you could basically recurse and break it down kind of like in a quad tree fashion. And then you can say for the top left corner, how much can I safely advance all of those rays at once? Um, and so on and so on. You can like recursively subdivide the view frustum, and so you can advance batches of rays recursively like that. And the upside is like you're making a lot less samples per pixels that way. Um, like I said, this might not be as practical on a GPU where you don't really want to use recursion, but on CPU, it works very well. If I toggle it, uh, this is my batch ray marching algorithm that's recursive, and you can see like it makes a huge difference, both in terms of like the number of samples per pixels and the frame rate. Like it is more than 3 times as fast. It's making like between a third and a quarter of the samples per pixel, and you lose nothing in terms of visual quality. I did a little bit of research, and as far as I can tell, nobody else has done this before. I mean, correct me if I'm wrong. Maybe somebody will watch this and they'll say like, actually, like I found a reference to this algorithm in the literature. But as far as I know, this is novel. Um, there are just prior art in like cone marching in the world of ray tracing. Um, but what's pretty cool is like when this with this technique, like at least on CPU, you can bring the cost of ray marching like I think a lot closer to the cost of like traditional ray tracing, but you still keep all the benefits of signed distance fields where you can have those really nice CSG operations. So it's just like a more efficient way to sample your SDF using recursion. At least for the primary rays. Like if you want to have like reflections, this technique will not help you make those reflections less expensive. But at least as far as the primary rays, like it seems like a huge win. Um, yeah, I'm thinking of making a blog post about this and open sourcing the code. Like it's not very complicated. I think just from my description, you might be able to implement it. But I'm still thinking like I might open source this. Um, I also thought like I I I also tried to implement an even more optimized algorithm that's approximate. So I have an algorithm number 4 here that I can toggle uh, that takes even less samples per pixels. This one is approximate. What's really cool is that sometimes it takes less than one sample per pixel on average. Um, and the way that this works is that basically I try to advance little patches of pixels as close as I can to the object. And once I get basically to the object, um, I'm shading a patch of say like for example 8 by 8 pixels all at once. So basically I don't I don't go down to the pixel level in the sampling and as you might be able to figure out like this, like I said, this technique is approximate. Like it works well here because this is flat shaded. There's no texture. Um, but for some types of scenes like this kind of approximate ray marching can be even more efficient on CPU. If you're willing to approximate, I can also like freeze the movement of it and toggle between the different algorithms. And here I'm toggling between like the batch ray marching and the approximate, and you you can't even tell the difference visually, which I think is kind of cool. Um, yeah, so I guess that's it for my presentation. As I was saying, like this is more useful on CPU than it is on GPU because on GPU like you wouldn't necessarily want to have like a recursive algorithm. However, I think there is a way to leverage this idea on GPU as well, which is that although on a GPU you maybe don't want to break down your view frustum recursively, you could think, for example, that you break down your view frustum into like patches of 8 by 8 pixels, and you try to trace those patches of 8 by 8 pixels. Like you try to evaluate your SDF and trace as far as possible. And basically you could do your rendering on the GPU in two passes. Like you do a pre-pass with say like 8 by 8 patches, and then you do a second pass where you use the distance from those 8 by 8 patches as kind of like initialization for the second pass. And I think in some cases that could actually greatly reduce the number of samples that you're performing even on GPU. Yeah, so that's it for my little presentation. I hope this was interesting to you. If you have any comments or questions, yeah, please please write.